Today we're going to be talking about energy, the invisible force behind, well, everything. Your whole day, from making breakfast to ordering your favorite overpriced coffee, mindlessly scrolling social media, to the bigger picture of powering AI data centers, everything we do and rely on is simply a transfer of energy from one thing to the next. But here's the thing, not all energy sources are created equal. Some are clean, some are cheap, some are dirty, some are basically science fiction. So today, we're answering what's the best form of energy today, 100 years from now, and in some future utopia where we harvest energy from space? Buckle up. To give some perspective on just how much energy we use today, 1 kilowatt hour is about the energy it takes to run one cycle of your average dishwasher. The average home uses about 30 times that amount per day. New York City, the largest city in the United States with over 8.4 million people, uses 11 million kilowatt hours per day. In other words, a lot of energy. Taking it just one tiny step further, Project Stargate will be the largest data center in the world, filling up an area roughly the size of Central Park in New York City, with massive buildings hosting millions of energy-hungry components. This data center is projected to be consuming over 144 million kilowatt hours per day, 24/7 when it's all said and done. You need to toast about 2.8 billion pieces of bread to consume the same amount of power that Project Stargate would in one single day. Or you could have the cleanest dishes mankind has ever seen, or light your clothes on fire. I hope this gives some perspective on just how much energy we consume and need today. And just know the trend isn't stopping. Energy demands are only growing. So now that we have a general understanding of how obscenely large the energy demand is today, how in this world, or actually I should say universe, are we planning on meeting these demands? Well, we could answer this question in a few different ways, so that's what we'll try to do. What's the best source of energy right now, today? What about in 100 years? What about in 10,000 years? In an ideal world, a utopia where energy is limitless and available to all at zero cost. And you may ask, why separate these categories? Why not just have one overarching analysis that covers all sources of energy? Well, I'm glad you asked, because comparing a black rock that can catch fire to harvesting rotational energy from a gigantic gravitational singularity spawned from the remnants of massive stars wouldn't be exactly fair. So, anyway, we'll evaluate each energy source on a simple 4-category scale: efficiency, cost, environmental impact, reliability. Efficiency is how good an energy source is at actually turning fuel into power. For example, if you pour 100 units of energy in, do you get 90 back? Do you get 30 back? Etc. Cost, we're talking about the real price tag here. How much it costs to not only generate power over time, but how much it costs to build the thing, maintain the thing, and run the thing. The fancy term is LCOE, but just think of it as the cost per unit of power. Environmental impact. This one's simply about how much damage a source does to the planet. Think of it as the environmental price tag, including everything from building, maintaining, and running. And finally, reliability. This is all about consistency. Can we count on this source 24/7? Or does it just vanish when it gets cloudy or calm outside? A green check for good, a yellow diamond for could be better, but not the worst, and a red X for With all that fun stuff out of the way, let's start with what's available right now. Our current energy arsenal includes coal, oil, natural gas, nuclear, solar, wind, and hydro. First up, we all know them, we all use them, fossil fuels. They currently account for about 80% of global energy consumption, so they certainly aren't going away anytime soon. With that being said, they are also non-renewable resources, meaning once we've used them all up, they are gone for good. Now, oil, we are going to immediately leave out of this conversation for a few reasons. You see, oil on its own makes for a phenomenal backup energy solution. It has a very high energy density, meaning it packs a punch. There's a significant amount of energy per drop, and it's very easy to store as a liquid. Throw it in a barrel and store it on some shelf for 5 years, you're good to go. However, there are two massive downsides that takes oil out of the running completely. One, the world relies on oil for a lot of different applications. As you know, mainly as a fuel source for transportation or backup power. And when so much of the world relies on this, there's a lot of fluctuation with supply and demand, leaving room for manipulation. OPEC, the Organization of Petroleum Exporting Countries, effectively controls over 80% of global oil reserves. Today, competition is heating up, and non-OPEC countries like the United States have been increasing their share in the global market, effectively reducing the control that OPEC may have or may intend to have on oil pricing. On top of that, investor manipulation, collusion between oil-producing countries and companies, and geopolitical tensions tend to impact price in a variety of unpredictable ways. Whatever the reason for oil prices skyrocketing, the end result is the same. The consumer gets absolutely reamed. Shipping, transportation, heating and utility bills, and the most common complaint, gas prices for your car, get really, really expensive. So yeah, there's a lot of drama around oil, and it certainly makes for a great energy source, but far from ideal. Next on the list is a black rock, which has its unique set of advantages and drawbacks. First, it's as cheap, well, as rocks. Developing nations are able to rely on coal in their early stages of economic growth because the infrastructure for mining, transportation, and power generation is everywhere and has been for hundreds of years. This makes for easy and cheap expansion compared to building brand new infrastructure for nuclear power plants or offshore wind farms, for example. However, coal consumption in developed nations like the United States is only going one way, and that's down. And for good reason. The environmental impact is, well, ungodly. I'm sure you've seen the cartoons or maybe even some old footage of coal-fired trains or the big factories with the big smoke plumes coming out of the top. Yeah, well, this smoke contains sulfur dioxide, nitrogen oxides, mercury, and a bunch of other poisonous chemicals that are all directly linked to respiratory problems and cancer. Great. So not exactly something we want to be pumping the air with and breathing into our bodies. Don't forget, coal mining on the surface can also contaminate water sources and permanently alter landscapes and ecosystems. So in conclusion, I think whether you want to believe if global warming is real or not, doesn't matter. What we can all agree on is nobody wants to be inhaling coal fumes into their lungs. So despite coal being cheap, widely accessible, and an abundant resource, the environmental impact is just overwhelmingly negative. Still, a great option for developing countries in their early stages of growth. Natural gas is where we really start to see some potential. Far lower greenhouse gas emissions than oil and coal. More efficient and reliable, versatile like oil as it's widely used for heating homes, buildings, and other industrial processes. I'm sure many of you pay a gas bill every month or at least live somewhere that may be the case. That's natural gas. It's wildly abundant and the infrastructure is well established, making for easier and cheaper expansion. So what's the problem? Do you see it? Here, let me zoom in a little bit more. Do you see it now? I know you can't smell it because you're behind a screen, but it smells like rotten eggs. So you could smell it if you were there. This is a methane leak. Unfortunately, methane is a colorless and odorless gas in its natural state. The rotten egg smell comes from an added odor to make methane leaks at least a little more obvious and detectable, rather than seeing and smelling nothing. Methane is no CO2 either. CO2 is harmful, but methane is over 80 times more potent than CO2. Now, the exact amount of how much methane leakage there is throughout the process of natural gas production and distribution is unknown for obvious reasons. However, estimates say it's between 1 and 3%. Now, this may not seem like a lot, but according to Rocky Mountain Institute, a methane leakage as low as 0.2% puts natural gas's climate impact on par with coal. Wow, we use the word ungodly with coal's environmental impact, so this is certainly problematic. However, there is good news. Technologies identifying methane leaks are drastically improving by the day. Satellite, drone, and sensor-based systems, all great steps in the right direction, but can be costly. On the surface, natural gas looks like a solid contender, and it is. There's no doubt about that. The metrics look good, but unfortunately, as we've already seen, sometimes there's just more than meets the eye. And well, that's quite the Achilles heel. If you've made it this far, consider subscribing. Or don't. So now we're going to transition into a much cleaner discussion. Let's take a look at some of the renewable options. Renewable energy, meaning energy sources that are replenished naturally or effectively infinite. We don't have to worry about running out of sunshine, wind, or water. First up, hydroelectric energy, using the flow or movement of water to generate electricity. Easily the most efficient form of energy so far because we don't lose any energy in the form of heat like we would from the heating of gas, oil, or coal, for example. For perspective, around 2/3 of the energy from burning fossil fuels is lost as waste heat. That's before the electricity even reaches its destination. But like natural gas, there is quite the Achilles heel. To build a hydroelectric system, a suitable location needs 2 bodies of water at different elevations. At different elevations, the water at source A will flow to the water at source B due to gravity. The larger the difference in these elevations, the more potential energy, the more electricity that can be generated. Only problem is we need 2 bodies of water. I think you can start to see where we're going with this. According to the International Energy Agency, around half of hydropower's economically viable potential remains untapped globally. Simply put, there are less good locations to build a dam than we may like. And as a result, planned hydroelectric projects are decreasing. According to one assessment, there is still plenty of opportunity for plants in developing and underdeveloped countries, but it doesn't always make a whole lot of sense, especially with no existing infrastructure in the relative area. Overall, a good option, especially to power local large-scale projects and infrastructure, but too location restrictive to be relied upon for a primary source of power. Next up, we have 2 other contenders in wind and solar energy. Very clean, very cheap, but the glaring problem, well, it's intermittent nature. Unless you live in Alaska during the summer months, the sun is only up for, well, half the day on average. So there goes 50% of the time we could be generating electricity. Oh, and don't forget about rainy, snowy, or cloudy days. So solar systems are really only able to produce electricity 25% of the time. Similarly, wind farms rely on the speed of, well, wind. So when it doesn't happen to be consistently windy, spinning that wind turbine around and around, you can expect that energy output won't be exactly reliable. Offshore wind farms are proving to be more reliable today due to the more consistent and powerful wind patterns out over oceans or large lakes, but even then, the cost to build, maintain, and operate these farms are double what they would be on land. Because of solar and wind's reliance on these natural processes, and not being able to simply control them with an on-off switch like natural gas per se, these sources rely on battery technology to temporarily store energy that is produced but not needed at the time. And albeit this does create a system that feels more efficient, but implementing and maintaining battery systems is expensive. Alright, I'm done. That's a lot of negativity, but there are some significant upsides. Solar in particular is set to become the largest renewable energy source globally by 2029, surpassing hydroelectric and wind. A big part of that is due to, well, I think you can see why. The prices of solar panels have plummeted dramatically. On top of this, policies around the world are increasingly favoring solar energy. This is allowing developing and even underdeveloped nations to get some skin in the game at relatively affordable prices. Although these sources aren't entirely reliable, they are extremely cheap and pair well with some of the resources we already talked about, like natural gas. When the sun isn't shining or the wind isn't blowing, we can simply flick the on-off switch of natural gas to fill in those gaps. This combination can be effective and is certainly less detrimental to our respiratory systems than a full-blown reliance on dirty fuels. But there is just one last source that we haven't talked about yet, and that's nuclear energy. Yes, that's right, we want that. Not literally a bomb, but this idea. Uranium-235 is the element used in atomic bombs. It's a very unstable element, as you might have guessed, which simply means it's prone to release a lot of energy under certain conditions. And as we know, atomic bombs are quite powerful, releasing a lot of energy upon detonation. We can take this same process used in the atomic bomb, but dramatically reduce the amount of uranium-235 and contain it in a controlled environment. This is the process of nuclear fission, the splitting of uranium-235, producing heat which can be used to generate electricity. And this is the process that nuclear power plants use today. Now, metric-wise, this may appear as a legit contender, but I think there's actually a stronger case under the surface as well. You see, 3 of the biggest drawbacks to nuclear energy today are the crazy long construction times, high upfront costs, and risks of catastrophic accidents like Chernobyl that scarred and literally poisoned people for the rest of their lives. Today, however, these three drawbacks are slowly and surely dissipating. It is true, the money and time it takes to plan and construct a nuclear power plant is very high, but a lot of this is due to the rigorous safety regulations and licensing procedures, all the red tape required to even begin construction. I think this stat kind of reminds me of how nuclear energy and the catastrophic accidents it can cause are viewed by the average person versus the actual reality of the situation. Most people are at least somewhat afraid of sharks, and if you're not afraid, then you're more afraid of a shark than a mosquito, probably. When sharks attack, it's scary, yet mosquitoes are responsible for far more deaths. It's honestly not comparable. Nuclear energy, surprisingly, is much, much safer than your fossil fuels on average. But the nuclear accidents that do occur, like the rare shark attack, obviously and rightfully scares the shite out of people and lawmakers. As you can see, when accidents do occur, the natural human tendency is to reduce construction of nuclear facilities dramatically, and that has been the case. However, today, technology and protocols ensuring safety have become so reliable that governments are once again leaning into the idea of more nuclear power plant construction. Countries like the United States are actively passing new regulations to streamline the development of nuclear power plant facilities, and presumably as this trend continues, the cost of nuclear energy should also decline, barring any sort of future catastrophic event. That rational fear has certainly kept prices of nuclear energy higher instead of following that natural decline we would expect as technology and efficiency improves. As we can see, solar has been trending down while nuclear has been stuck. So as these two drawbacks begin and continue to be alleviated, there's really only one left that we haven't yet discussed, and one that governments and people around the world are deeply and rightfully concerned about: toxic waste. When the process of nuclear fission occurs, the process that actually happens in nuclear reactors that produce electricity, there's a lot of harmful stuff that remains as a result, or so we thought. For the most part, this problem is wildly overhyped. This graphic does a great job showing that nuclear waste is buried beneath the ground. The more toxic the waste, the further beneath the ground it is stored. As you can see, about 99.75% of nuclear waste is considered very low level, or intermediate level waste. So basically all of it. That's the Tower of Pisa right there as a reference. This is an oversimplification. But no, we don't need to get into the weeds. This waste, although not ideal, is pretty easily handled. Most of it can be stored in near-surface underground facilities and eventually even just be thrown out in ordinary trash. However, some of this waste needs to be stored for, no lie, millions of years before it becomes safe to handle. But again, that's just a very, very small percentage. Ultimately, as costs start to come down and the nuclear power plant permitting and building process becomes streamlined, nuclear energy is our best option. However, with that being said, nuclear energy on its own just simply isn't capable of providing enough energy. Therefore, a healthy, diverse energy portfolio is necessary, and that's exactly what we've been building. Solar and wind projects continue to expand, and natural gas can be relied upon to fill the gaps. And this is all great now, but what about in 10, 50, 100 years from now? As we saw earlier, fossil fuels will be pretty much gone. And if we went from basically no AI 5 years ago to literally AI everything today, then only God knows where technology will be and how much energy the world will require in that distant future. So speaking of that distant future, what is the best energy source 100 years from now? We are going to work under the broad assumptions that 1, major technological advancement continues to happen at a similar rate as today. 2, we haven't left the realm of physics. And 3, politics will still be messy and play a major factor in keeping some energy sources more expensive than others, similar to all that red tape that we saw in the nuclear energy example. Alright, so 1 century from now, there are really 5 sources that seem feasible. One of them we already talked about in great detail actually, solar, except with a bit of a catch. Space-based solar is the idea that we can actually avoid one of the biggest downsides of solar in that we rely on the sun to be out and shining. Instead, we could capture this solar energy in space via some form of orbital infrastructure made up of satellites equipped with solar panels with direct exposure to sunlight 24/7. No need to worry about the rainy days or the clouds coming out. Skip all of that, get out of our atmosphere, and get direct exposure to the sun. Now, this sounds absolutely beautiful in theory, right? But the problem remains, how do we get this energy collected in space? Because that is feasible today. We do have satellite systems in space orbiting our planet, but how do we transfer that energy to our homes and large data centers? Well, the running theory is that electricity can be converted into microwaves or laser beams and transmitted to receiving stations on Earth. Japan, United Kingdom, and China are actually running experiments on this technology right now, but it's still unproven at scale. Downside, well, you'll have to build a massive infrastructure that orbits the planet. So yeah, it would be rather expensive. Because these technologies are more speculative than proven at this point, it's important to remember that giving concrete ratings for our categories could vary drastically depending on the rate of technological development. Disclaimer aside, the next energy source, also having to do with sunlight, is artificial photosynthesis. Photosynthesis being the process plants use to convert sunlight, water, and carbon dioxide into usable energy. If you took a biology class at some point in your life, you've probably seen this equation. Without getting too into the details here, just imagine a system similar to a solar panel that takes in light and carbon dioxide to produce usable energy. These systems could be deployed virtually anywhere, but would still rely on exposure to sunlight. Now, there is research being done into using artificial light instead of sunlight to take our reliability from roughly 25% to 100%, but again, that's unproven and there's still a long ways to go. And this comes back to the same problem that we had with solar, right? Until we can get that reliability rate up, it may just play a similar role to what solar does today. A great way to passively collect and store energy, but too unreliable for a primary energy source. Two more sources of energy that deserve honorable mentions but no further analysis are deep geothermal and tidal or wave power. Deep geothermal involves using the heat from Earth itself, deep underground, to power heating and cooling applications similar to natural gas. However, there are risks like inducing earthquakes. In 2017, a deep geothermal plant in South Korea was shut down after probably causing a magnitude 5.5 earthquake. Nice. Anyways, tidal and wave power is another way to take advantage of Earth itself. Vast oceans that cover over 70% of our planet with consistent and predictable wave and tidal patterns seems like a no-brainer to me. Using the motion of waves and tides to generate electricity. Sounds great. However, both of these energy sources, deep geothermal and wave energy, have spectacularly high initial costs, potentially serious environmental impact, and rely on specific geographical conditions. So both don't seem too likely to be top candidates for the primary energy source of the future. Finally, and most promising, is nuclear fusion. Not to be confused with nuclear fission, the nuclear energy that we refer to today. Nuclear fusion is the opposite of fission. Fission splits atoms apart, while fusion combines atoms together, both releasing a lot of energy in the process. Now, we talked about fission leaving behind some nasty nuclear byproducts that could stay radioactive for millions of years. Well, fusion has none of that. In fact, the worst byproducts that fusion produces are potentially safe to recycle and reuse after 100 years. Albeit still a long time in human years, but better than a million. So nuclear fusion is essentially a cleaner version of nuclear fission that can also use more abundant resources. Fission uses uranium-235, which makes up only 0.7% of all natural occurring uranium. Fusion, on the other hand, can use deuterium, which is abundant in seawater. So in essence, unlimited. So this is kind of a full circle moment, right? Nuclear fusion is setting up to be the world's most promising primary source of energy. The stars that surround us in the galaxy and the sun that powers our entire solar system rely on nuclear fusion. The heat and light emitted from stars are a direct result of this process. However, as you might expect, it presents quite the engineering hurdle. Replicating the conditions of the sun's core on Earth requires temperatures exceeding a measly 150 million degrees Celsius. Hotter than lightning, lava, and believe it or not, even the bottom of your old Apple laptop. If you know, you know. So you could imagine creating these conditions takes a lot of energy, raising questions if there is a sustainable and cost-effective way to get more energy out than we put in to create these sun-like conditions in the first place. Fortunately, there have been some big strides made in the field, and there is certainly growing confidence amongst the nuclear fusion community. The amount of nuclear fusion startups has been skyrocketing, and one company in particular, Commonwealth Fusion Systems, CFS, has raised over $2 billion and has even received power purchase agreements from Google to power their power data centers in the future with, you guessed it, nuclear fusion reactors. These reactors aren't operational now, but CFS is aiming to have a commercial nuclear fusion power plant in the early 2030s, so I guess we'll just have to see how things develop in the coming years. But either way, nuclear fusion is no doubt the best power source of the future, at least in this moment, assuming no black hole magic in the next 100 years. Essentially, clean, limitless, anywhere in the world, 24/7, and prices will naturally only come down with time as technology improves. Sounds pretty good, but believe it or not, there's some ideas that sound even better. We might just have to drop some of the assumptions that we made for our last segment. Yep, that's right, that is better. We are now entering Utopia, a distant future where energy is unlimited at essentially zero cost. Utopia, a future that is, for the most part, science fiction at this point. Although some ideas are more feasible than others, there's really no objective way to tell which source is better because they could all be perfect in theory, but we're going to try to rank them on our scale anyways. And to do this, we're going to introduce two more symbols: fire for perfect and question mark because we really don't know the answer to it. Remember, in Utopia, in simple terms, we want energy that is unlimited, available 24/7, completely clean, and accessible anywhere on the planet. So here we go. The Dyson Swarm, or partial orbital solar harvesting. Massive orbital platforms that collect solar energy 24/7 and beam it back to Earth via microwaves or lasers. Think solar collectors built around the sun. Avengers Infinity War reference here. This shows it best. But instead of dwarves using this energy to create Stormbreaker for Thor, we can use it to power civilization for 500,000 years. No lie, the sun emits enough energy in 1 second to power all of civilization for 500,000 years. But engineering a platform this close to the sun and then transferring that energy 94 million miles to Earth isn't exactly feasible at this moment. And as you can imagine, engineering difficulties of 1, being that close to the sun, and 2, having Earth that far from the sun is quite the problem. You'll notice that engineering difficulties tend to be a recurring theme throughout this science fiction portion. 2, we have antimatter energy. Antimatter is the mirror image of regular matter, composed of antiparticles that have the same mass but opposite electrical charge. All you need to know is when antimatter collides with matter, they destroy each other. They annihilate each other, effectively converting all of their mass into pure, clean energy. Kinda like a nuclear bomb, but without the destruction and without the poisonous nuclear radioactive waste. While the early universe likely contained equal amounts of matter and antimatter, we haven't observed significant amounts of antimatter in the universe, and this remains one of the biggest mysteries in physics. So if we can't find it, we definitely can't collect it, but we can create it in very expensive machines. Right now, creating even a little bit of antimatter is unreasonably expensive, but with time, you never know. Converting mass into pure energy does seem like an intriguing opportunity. 3, nuclear fusion. Yes, that's right. Nuclear fusion is back on the list. You know, maybe we are closer to a perfect energy source than we may have thought. As technologies advance, we are essentially creating and maintaining a living and breathing sun on Earth. So instead of engineering an Infinity War style rotating chassis around an active star 100 million miles away, why not bring the star to us? 1 bathtub of seawater and you have the fuel to provide energy for a lifetime. If we crack fusion, we crack energy. And now we've reached our final form of energy, and that's black hole spin energy. Yes, you heard that right. Probably the most perfect form of energy that exists in this universe, but also the most science fiction. What else would you expect, right? Black holes are regions in space where gravity is so incredibly strong that nothing, not even light, that travels at 186,000 miles per second can escape. A place where time and space are physically altered, bending the rules of physics that we live by on Earth and challenging our understanding of what is possible in such extreme conditions. A rotating black hole stores immense energy in its spin, up to 29% of its mass as rotational energy. For perspective, a black hole the mass of our sun, which is actually a very, very light black hole, yes, you heard that right, would store enough rotational energy to power Earth for billions of years. And keep in mind, there are black holes that are millions to billions of times the mass of our sun, with entire galaxies subject to their gravitational pull, including our very own Milky Way galaxy. Now, if we were to ever reach this sort of technological ridiculousness, let's just say we probably wouldn't be worried about achieving a primary energy source for AI data centers. We'd probably be trying to solve problems on a cosmic scale, like providing energy for the hundreds of planets and hundreds of galaxies that we inhabit at that point. So yes, this energy source is theoretically perfect, but is very simply not physically feasible with our current understanding of how the universe works. But one day maybe. You never know. So in conclusion, we have the three big winners right here. Today it's going to be nuclear fission. Tomorrow, in 100 years, it's going to be nuclear fusion. And in Utopia, it's probably also going to be nuclear fusion or harvesting energy from rotating black holes. Now, obviously, as you move up the ladder, things tend to get more and more unrealistic, but it is interesting to see what is possible on this planet. Going from steam locomotives and trains, using a flammable black rock, to now creating controlled star-like environments on Earth. The technology and capabilities that we have accomplished are just fascinating, at the very least fascinating. So I hope this video gave you some insight on the various energy sources that our Earth has to choose from, whether that be science fiction or not. And I also thought this investigation would be useful for potential investment opportunities in the future. Data is the currency of this planet right now, and to produce data, you need power, and the data that we're producing today needs a lot of power. So with that being said, maybe this is a potential opportunity to invest in the pickaxes and shovels instead of the gold. One day, energy will be a commodity. It will be free and limitless for everybody. But today is not that day, and today isn't close to that day. So for the time being, you can charge a lot for clean energy. I hope you all enjoyed the video. If you did, give it a like and let me know what your favorite source of energy is. Maybe let me know if I missed one. Biomass, because I didn't feel like talking about it. That's it from me. See you in the next one. Bye-bye now. Bye-bye. See ya.